So while we're on the topic of atomic structure, just keep in mind that electrons are the ones that are going to play a large role in the way that these atoms behave. Remember that energy is the potential to cause change. So we're really looking at potential energy based on its location or its structure when we're dealing with atoms, talking about chemical energy. Um, so electrons will actually differ in their amounts of potential energy based on how far away from the nucleus they are found in a particular point in time. So we often discuss electrons in a handful of different models in terms of where they're located relative to the atom's nucleus. We can talk about orbitals, um, we can talk about electron cloud, which is really just they're there somewhere, or we can talk about energy levels. We will spend some time when we get to photosynthesis really focusing on that idea of energy levels or energy states, because that is going to be a big indicator for how chlorophyll molecules are able to take in energy from the sun. So each energy level or electron shell or orbital generally has a certain amount of energy associated with it, and those electrons move between those levels based on whether or not they're gaining or losing energy from the environment. So it really is the chemical behavior of those atoms and the distribution of those electrons in those shells, in those levels, that determines its ability to interact with other atoms. So when we look at this, the most important electrons from a chemical standpoint, from a building of compounds, chemical reactions idea, really are those valence electrons. And these are the ones that are in the outermost shell, your valence shell, because they are the ones that aren't being shielded by anything else. And so they're the ones that are available for chemical bonding to occur. So when we talk about those valence electrons, it really is that incomplete valence shell that drives atoms to participate in chemical bonding. So all of those atoms really are striving to reach that full valence shell, that full octet, to get a electron configuration similar to those noble gases at the end of your periodic table. And so in order for them to do that, that means that they're going to have to come together, stay together, and they get held together by these attractions, these chemical bonds, either by sharing or transferring valence electrons with other atoms. So when we look at chemical bonding, we can talk about sort of this category of strong chemical bonds versus weak chemical bonds. And it's really just a matter of how much strength does it take to be able to break that bond, break that connection between those atoms. So one of the strongest chemical bonds are covalent bonds, where we're sharing pairs of electrons between the valence shells, between atoms. And these covalent bonds can be single, where each atom in the chemical bond is contributing a single electron. As a result, they're sharing a pair of electrons between those two nuclei. Double bonds, so sharing two pairs of electrons, or a total of four. And a triple bond, where we're sharing three pairs of electrons, or a total of six. So when we look at chemical bonds, we're talking about, our covalent bonds, I should say, we're looking at these molecules consisting of two or more atoms that are held together by chemical bonds. So we talk about a molecule of water, molecule of carbon dioxide, that kind of thing. And these molecules can be polar or nonpolar based on the electronegativity of the atoms that are involved. So when we look at electronegativity, it's really the atom's ability to attract electrons. Are they sort of both equally capable of hanging on and attracting those electrons? Or is there some unequal balance there? So if they are equally sharing, the electrons are sharing the same amount of time around all nuclei of the atoms, then we would talk about it as a nonpolar molecule. If one atom is more electronegative than the other, resulting in that unequal sharing, something like what we see with water, where those electrons do spend more time in one part of the molecule than in another, you get these sort of partial charges as a result. And that's just because you get something like oxygen who's hanging on to those electrons remember electrons are negative more of the time, and so that end of the molecule gets the partial positive. The hydrogens aren't hanging on to them quite as often, and so their protons in their nucleus are shining through a little bit, and you get those partial positive charges. Be very careful when you are writing out charges on an atom to be very explicit as to whether it's a partial charge, which you'll get that little sigma sign, sort of squiggly S, as opposed to just a positive and a negative, because just writing positives and negatives can make it a little more confusing. Are you talking about a partial charge, or are you talking about a full charge on that molecule? And we can talk about ions, right? And even polyatomic ions, where you're getting multiple atoms linked together, but there's still an overall positive or negative charge based on the electrons being shared, or excuse me, whether the electrons are being lost or gained, as opposed to here, we're looking at the sharing of electrons, it's just not an equal share. Ionic bonds also fall into the strong chemical bond category, so it's going to take a considerable amount of energy to break these guys. Covalent are the strongest, ionic come in next, and here we're talking about those ions, right, or polyatomic ions, a charge on a molecule. So ionic bonds are being formed when we transfer electrons from one atom or one set of atoms to another. And so there's a charge to them. Your cations are your positively charged ions, an anion would be a negative charge, and an ionic bond, just by definition, is the attraction of an anion and a cation. And so when we look at the compounds that are formed by ionic bonds, we typically call them salts, something like sodium and chloride. So sodium only has one electron. As a result, it's more likely to lose it than try to find 8 to fill itself up, and it's a lot easier to lose that one than trying to even find somebody who can share 7 more. So it transfers its lone electron to the chloride ion. When it gives up that electron, it now has an overall net positive charge, thus being a cation. Chloride takes it. Again, it's a lot easier to go find one to fill up its shell than to try and dump 7 of them. And they also tend to be more likely, based on their electronegativity, to completely hold on to those electrons as opposed to sharing them. And so the chloride ends up with an overall net negative charge, thus an anion. And these guys are electrically connected to each other, positives, sort of like magnets, positive and negative. And so we get sodium chloride, which most of us probably know commonly as table salt. Then we can talk about weak chemical bonds. So these guys are reinforced really more about the shape of these large molecules and these molecules adhering to each other. So when we talk typically about strong chemical bonds, they're usually interatomic between atoms. When we look at weaker chemical bonds, these are usually intermolecular or between molecules. One that you're probably most familiar with is this idea of a hydrogen bond. This is going to come back when we talk more about water, which is probably where you've learned it before. So hydrogen bonds form when a hydrogen atom is covalently bonded to an electronegative atom, like the oxygen in the water, as a result, producing those partial charges. And so those partial charges, the positive from a hydrogen on one atom is attracted to a partial negative on another molecule, and you get the hydrogen bond that forms in between. So it's still going to take some energy to break these, which is where a lot of the water properties are going to come from, but not nearly the amount of energy that it would take to break the bonds between atoms like a covalent or an ionic one. Van der Waals forces, this is another one that is also a weak chemical bond that occurs between molecules. So when those molecules come together, you can actually have sort of typical, more spherical ideas of atoms or molecules, and they don't have any partial charges naturally within their typical shape, but if they get closer together, that actually forces them to sort of bend and adjust because of the electron density, and so it pushes those electrons outwards, and so you get these sort of temporary hotspot charges asymmetrical electron distribution within those molecules or those atoms. As a result, you get these sort of weak sort of dipole moments, and that ends up allowing some of these molecules to stick together temporarily. Again, weaker than you would typically see even with a hydrogen bond. Something to consider as we're talking about these atoms and molecules forming is that when compounds get created, they need to allow for those electron densities to be as dispersed as possible. Electrons are negatively charged, they don't like each other, they don't like being forced together, and so they won't compact any more than they need to. And so what that results in are very unique shapes to molecules. And those molecular shapes in biology are incredibly important in the way that they function. So biological molecules in a living thing, these are our communicators. Everything that we do from one cell to the next in order for it to communicate, especially in a multicellular organism, to coordinate function, is done at a molecular level. So biological molecules are recognized from one cell to the next based on their shape. And those molecular shapes are really important in the way that they do their job. So when we look at something like this example of natural epinephrine versus morphine, so painkillers, right? Excuse me, a natural endorphin versus a morphine molecule. When we go to make pharmaceuticals, we have to make sure that in those receptors, so in those sort of communication connections within your cell membrane, that we are producing something that can still be recognized and elicit the same reaction within a cell based on the shape of those receptors. Sort of think of it kind of like an enzyme idea with a lock and a key. I need to be able to have the right portion of grooves and peaks within that key structure to make it still do its job. So it needs to be close enough. And so your natural endorphins are pain relievers. Morphine's job as a pharmaceutical is to do the same thing. So in order for them to still work as painkillers in your brain cells, I need to have developed this particular structure in the same functional shape. And so the endorphin is much bigger out here, but that's not what's being utilized by that receptor. So we just need to be able to create a molecule that fits within that receptor, turn that key essentially, and create the same response inside the cell. So it's very important that that shape is consistent, at least in terms of the portion that is biologically active. Chemical reactions. This is going to be the setup for our entire discussion about metabolism. Metabolism is the overall culmination of all the chemical reactions that happen in your body. So let's make sure we know what that means. Chemical reaction is just the making and breaking of chemical bonds. So we'll take those reactants, those starting molecules, input some energy in order to break the bonds in that reactant, pull those atoms apart, rearrange them into those products, and make those final molecules at the end. Keep in mind that when we talk chemical reactions, energy goes in, energy also comes back out when we form the products. The question then becomes how much energy needed to go in versus how much energy came back out. And that's where we can have discussions about things like endothermic and exothermic reactions. We'll actually use the terms endergonic and exergonic. But if you've heard endothermic and exothermic before, it's the same basic idea. We're just talking about energy in versus energy out using that goner ending to the term, as opposed to therm, meaning specifically heat. Most chemical reactions that are occurring, especially in biological systems, are actually reversible. And so if we leave them go long enough, they will reach that level of chemical equilibrium where the production of reactants to products in one direction ends up equaling out or balancing out the opposite or reverse reaction in the opposite direction. So you'll end up seeing double arrows, one arrow this way, one arrow this way, when you look at those reversible reactions. One of the things that we'll talk about later when we get to metabolism this year is just talking about how your body almost works to prevent that chemical equilibrium, because although we need those molecules to move back and forth, or at least they're capable of doing that, we don't necessarily want that to happen. And it's really about an energy cascade that we need to be able to set up in order for that to work. So we'll come back to that idea later this year.